right, this next section we're going to be covering parallel RC circuits. Now remember, the same rules apply. We're just going to continue to move through it. I'll give you guys the equations. We'll work through them. I'm going to go through two examples of parallel circuits. The last one's going to have an extra capacitor this time instead of where the series one had an extra resistor. And then once we're done with that, we'll move into the series parallel circuits, and I will do another video on those, so everything will split up. So all in all, there's going to be, let's see, there's 3, 4, 5 videos total. A couple of them are kind of short, so it shouldn't be too long. Like I said, there'll be a couple of times to watch them through, take your time. This is basically the whole week's worth of lecture condensed into 5 videos. So just kind of go with that and pause, repeat, play over, do what you guys need to do, and reach out for help. All right, so let's go ahead and get going. So we're going to use the same rules, the same conversions that we've been using for the other problems as well. So our opening circuit we're going to have will be this. So we've got parallel RC circuits, we've got our generator, and we've got a resistor, and we have our capacitor. Now the capacitor is going to be 150 nanofarads. The resistor is going to be 360 ohms. Our generator is going to be 4 volts peak at 640 hertz. Now the things we're going to be looking for in this one is we're going to be looking for the reactance total of the capacitor, and that's going to be in kiloohms with its angle. We're looking for the total impedance of the circuit, which is going to be in ohms at an angle. Our current total is in milliamps. We're looking for the current of R1 in milliamps, and the current of cross capacitor 1 also in milliamps. So those are the things we're going to be looking for, and this is our circuit to do it. So again, we're just going to go through things the exact same ways we did before. So the capacitive reactance is going to be equal to 1 over 2 pi FC1, okay? Where this is equal to 1 over 2 pi times 640 times 150 nano. So X of C1 is going to be 1.657 K at negative 90. Okay. Now we're going to go through, we need to find our impedance total. So again, we're going to look at this, and we have a parallel circuit. So since we have a parallel circuit, what we need to do is we're going to use the reciprocal rule and solve with using our reactance and our resistance, just like we would do if there was 2 capacitors or if there was 2 resistors. It's going to take a little bit more work because we're going to have to do some more conversions back and forth, but it's not that bad. Okay, so we start off with our formula. It's going to be 1 over the reciprocal of our resistance, which is 360 at 0. We're going to add that to the reciprocal of our reactance, which is 1.657 K at negative 90. So now when we look at this, when we take the reciprocal of these guys, remember, we do have these new terms for these guys. We have, oh crap, I just dropped my papers down. Let me pick them up real quick. Okay, so remember that resistance, its reciprocal is conductance. Reactance, its reciprocal is susceptance. And then impedance, its reciprocal is admittance. So we're going to be using all these guys to solve for these. So the first thing we want to do is we want to kind of simplify this equation down a little bit. So we can apply the reciprocal to both sides. So our impedance is going to turn into the admittance, and then that leaves us with this, which doesn't look quite as scary, and there's not as lot going on. It's easier to solve this guy. Okay, so now what we're going to do is we're going to find the conductance, we're going to find the susceptance, and then those are going to add together so we find the admittance of the entire circuit. Okay, so now as we go through these, we end up with, so the total susceptance of the, the total admittance of the circuit is equal to 2.778 millisiemens, and this here is our conductance. This is our admittance. And then this is going to end up being 603.5 micro at 90 degrees. This guy's at 0 degrees. And again, this is measured in Siemens. And this is our susceptance. And then this one is plus J, or sorry, plus, because when we go through this problem of converting him, this guy comes out to be a positive value. So plus 603. Okay, so now we have these values and they're polar, so we're looking at the function. So right here we're having to add these functions. So these two we need to convert into the rectangular equivalents. That way we can go through and solve for these guys. Okay, so now when we come back and look, we have a special case. So we have our conductance, and just like we have before, we can still make these conversions. So we have an angle of 0. So that means this is pure resistive, or pure real. There's no imaginary values to it. So this value, we're going to convert into rectangular, is equal to 2.778 milli plus J of 0. Okay, this value, we're going to convert into rectangular. It's at 90 degrees, so that means we are at a plus J of the 603.5 micro, and there is 0 real component to it because we're at the positive 90. Remember, this is one of our quick conversions we can do. So now we have the total admittance of our circuit is equal to this value plus this value. So now we just need to combine like terms together. So we have this guy and this guy, we're going to combine together. That's going to give us our real. We have this one, the J0, and we have the J603 micro that we're going to combine together, and that's going to give us our imaginary. So this equivalent circuit is equal, or the admittance of this guy is 2.778 milli plus J of 603.5 micro. Okay, now that's good. So now what we want is we want this total answer into impedance. So which means we're going to have to take the reciprocal of this whole equation again to go back into impedance from our admittance, which means that these guys are going to be divided again. So since we're doing division, this one needs to get turned into polar notation. Okay, so again, we will go through and we're going to convert it just like what we have been doing. So now the admittance total in polar form is going to be the 2.778 milli. We're going to square that. We're going to add that to the 603.5 micro. We're going to square that. Then we're going to take the square root of that value, and that's going to give us the magnitude of the polar version of this. And then for the angle, remember, we're going to take the arctangent of 603.5 micro divided by the 2.778 milli. Now remember, this one right here, the top part of it is positive because this value over here is positive, and this is also J. Okay, so when we flip everything back around, yes, it's going to be negative, but that's because we're taking the inverses of everything. It's going to flip all this stuff for us. But right now, we have to just go with the polarity of it is in this part of the equation. So we end up with the admittance total in polar notation comes out to be 2.843 milli at an angle of 12.257 degrees. Okay, Now we're going to take the reciprocal of both sides of this, and this is going to turn this back into our Z total, our impedance, and then we're going to take the inverse of 2.843 milli at an angle of 12.457. When we finish doing that, our Z total comes out to be 351.741 at negative 12.457 degrees, and this is in ohms. So again, if we come back and look, we have to check and make sure, does this answer make sense? So we have 351 ohms is our final value across it. So if we come back and look at our original circuit, we have 360 ohms in parallel with 1600 ohms. So yeah, our value is going to be smaller than this value, but it's going to start getting fairly close because this is starting to, get up there compared to our other value. So yeah, we should see a value just slightly less than our 360, which is what we got. Okay, so now we're going to continue on just like what we did before. We're going to solve for our I total. So in this case, we have 4 volts at 0 degrees. That's going to be divided by the 351.741 at negative 12.457. And that's going to give us a current of 11.372 milliamps at 12.457 degrees. Now, we want to look at the currents for the other components. So the current for R1 is equal to, now remember when we're looking at this guy, we have voltage divided by resistance. These guys are in parallel, so these two are going to both have access to the 4 volts. They're not going to split it up in any way. So we come back down here, we go to our 4 volts at 0. We divide that by our 360 ohms at 0, and that is going to give us 11.111 milliamps at 0 degrees. Okay, IC1 through the capacitor, same thing. It's going to be 4 volts at 0 degrees. And in this time, we're going to be divided by the reactive capacitance, which is the 1657 at negative 90. And that's going to give us a total of 2.414 milliamps at 90 degrees. Now again, we're looking to a situation where we used Kirchhoff again. Okay, so our total current says we're at 11.3 milliamps, roughly. Okay, when we look down, well, we have 11.1 and 2.4. That's going to give us 13 milliamps. Again, they can't just add because they are out of phase. So we want to be able to check this guy using Kirchhoff's current law. So we want to check using Kirchhoff's current law. So remember, here we have our I total is going to be equal to the IR1 plus I capacitor 1. So again, let's write down our values. So we have 11.372 milli at 12.457 is equal to 11.111 milli at 0 plus 2.414 milli at 90. Now, because we're adding, we have to convert these guys into rectangular, and we can do a quick conversion because we are at 0 and at 90 degrees. Makes it easy. We don't have to go through the whole process. So this ends up being so we have 11.372 milli at 12.457, because remember that's what we're trying to double check against, is equal to 11.111 milli plus J of 2.414 milli. Okay, because remember this guy's positive, so this is going to be a positive J. And now we take this value here, since we have just a real value and an imaginary value, we're going to convert that to polar. So we have 11.372 milli, and I'm not going to bother writing that down for a second. We're just going to convert this. So we end up with 11.111 milli squared plus 2.414 milli squared. And then at the angle of 2.414 milli over 11.111 milli. And so we end up with, this is going to be equal to 11.370 milli at 12.258. And I just realized I goofed. Looking back at my notes, these guys, this is 257, not 457. So I'll make that correction up here as well. Sorry about that. There we go. Everything else should work out good now. So we can double check our answer. So we have 11.372 milli at 12.257 degrees is equal to this value. Close enough. We're good. So again, like I said, when we're using Kirchhoff, we just have to add the values together, whether it be current, whether it be voltage, and we have to convert those individual polar values into their rectangular equivalents, combine anything together, and then convert it back. And then we can double check everything. And really, that's where it comes down to is, it is as simple as that. You just have to do a couple of conversions. You just have to remember, what do I need my answer in? Does it need to be in polar, or does it need to be in rectangular? Just depends on how you're going to use it later. Sometimes you might not have to convert it at all if you're not going to use that value again. No sense in doing extra work. Okay, next circuit. So this time we have our supply. We have 6 volts sitting across it, and we have 2.894 kilohertz. We have R1, which is 510 ohms. We have capacitor 1, which is 11 nanofarads. And we have capacitor 2, which is 220 nanofarads. So what we're going to be wanting to find in this one is we want to know our X of C1, our X of C2, so the capacitive reactance. We want to know the Z total, our I total, our IR1, our I capacitor 1, and the current through capacitor 2. So our capacitive reactance for 1 is going to be equal to kiloohms at its angle. Capacitor 2 is in ohms at an angle. Our total impedance is in ohms at an angle. Current total is in milliamps. IR1, I capacitor 1, and these guys are all milliamps. So we want these 3 to those values. So that's what we're looking for. Okay, same process that we're going to go through. Remember, capacitive reactance is equal to 1 over 2 pi times the frequency and its capacitance value. So X of C1, 1 over 2 pi times 2.894 K times 11 nano. So X of C1 is equal to 5K at negative 90. X of C2 is 2 pi times 2.894K times 220 nano. So X of C2 is 249.976 ohms at negative 90. Okay, so that takes care of our first two. Now the next one we want to look at is our impedance. So the impedance total is going to be everything of the whole circuit, and they're all in parallel, so we're going to treat them with the reciprocal rule. So we have 1 over 510 at 0 plus 1 over 5K at negative 90 plus and I'm just going to round this up just to make it look a little easier, 250 ohms instead of everything with the other value. This is exact. We're not losing anything. This is where I wanted it to be. Again, this goes back to rounding based on your calculator. So, but these are the values that I wanted. That's why I set them up this way, just so it could be a little bit cleaner when we're solving through this guy. So again, we're going to take the reciprocal of both sides. So we end up with the admittance, and then we're going to solve for all of these guys just to make our lives easier. Okay, so the admittance total is going to be equal to 1.961 milli at 0. That's going to be added to 200 micro at 90. And this is going to be 4 milli at 90. Okay, so again, we're going to combine these two guys together because they have the same angle. So we end up with 1.961 milli at 0 plus 4.2 milli at 90. Okay, so now we know we're going to have to take the reciprocal of this guy again. So we need to convert this value here into rectangular. So we'll slide this up out of the way. So the admittance total that we have is going to be equal to 1.961 milli plus J of 4.2 milli. Because remember, these are easy conversions we can make. This is a positive J. This is no J. This has no resistance, no real value. So now we're going to convert this guy into polar. So we're going to take the 1.961 milli, square it, and we're going to add that to the 4.2 milli value and square it. Take the square root of both sides. And then the angle is the arctangent of 4.2 milli over 1.961 milli. So our total admittance of this circuit comes up to be 4.635 milli at an angle of negative 64.972. Sorry, that's a positive value. And then we're going to take the reciprocal of both sides. So we end up with our impedance total. And the final impedance of our circuit ends up being 215.75 ohms at negative 64.972. And again, so we have 215 ohms. Let's go back up and look at our circuit. We have a 510 in parallel with a 249 in parallel with a 5K. So it's going to be less than the 250, and we're at 215. So that's our impedance total. Now we come back through. The current total is equal to our voltage at 0 degrees divided by the 215 and a quarter, or 3/4, at negative 64.972. So the current comes out to be 27.81 milliamps at 64.972 degrees. And that is our current total. Now we want to know the currents through each individual component. So IR1 is going to be equal to the 6 volts. Since they're all in parallel, they're going to have the same voltage divided by its resistance or impedance. So IR1 is equal to 11.6765 milliamps at 0 degrees. Okay. IC1 is equal to the same voltage divided by its reactance, which is 5K at negative 90, and that comes out to be 1.2 milliamps at 90 degrees. And IC2, same thing, 6 volts at 0, divided by its reactance, which is 250 at negative 90, and that comes out to be 24 milliamps at a positive 90 degrees. So that gives us everything. And then again, we can go through and Kirchhoff this one. So I'm not going to go through it on this one, but again, you can, and everything will work out again to where our currents are going to, the current total is going to match the sum of all the currents going through each of the circuits. So like I said, go through, feel free, use this video, pause it as needed, work it through yourself when you get at the beginning of the problem. Work it through yourself, write down any questions that you have, and then either wait till the time for theory and we'll get on together and discuss it, or we can go through and like I said, individually message me or get a hold of me somehow, either way, through text, call, email, anything like that, and I will offer up the assistance I can. And this is how we handle parallel circuits. The next video that we'll have is going to teach you guys how to get through the series parallel. Now we're going to combine these two methods and just add them together, just like what we've been doing. Again, the hard part is going to be the parallel and keeping those values, the same. Just like I said, go step by step by step. Don't try and skip through things. Make sure everything's listed out and in their correct units, and then make sure to double check. Do my answers make sense? These things are in parallel. What should the value be? Oh, well, if they're in parallel, the value should be smaller than the lowest resistor. Did I get that? Okay, good. Then I'm probably on my way. And then also, remember the rules too. If the resistance value is a lot higher than the capacitive reactance value, then we're going to start to see an angle that's getting closer and closer to 0. If the capacitive reactance value is a lot larger than the resistive value, we're going to see that angle shift and it's going to start heading towards negative 90 degrees. And also remember, if they are equal, we should see a 45-degree angle between the two of them when it's all said and done. So anyway, that's parallel circuits. And like I said, if you do have any questions, please let me know and we will get things done as much as possible.